Electron configuration. There's 4 quantum numbers that give us the address for the electron, but it's inconvenient to write out all the possible quantum numbers, especially for atoms that contain many electrons. So instead we use electron configuration to show how the electrons are distributed among the various atomic orbitals. So the big number 1 denotes the principal quantum number n. The letter denotes the angular momentum quantum number L. And the superscript, or the exponent, denotes the number of electrons in the orbital or sublevel. An orbital diagram shows the spin of the electron. So again, we have the principal quantum number, the angular momentum quantum number, and then the box or just a line could represent the magnetic quantum number, and then you have the arrow to show the electron, and an arrow down would be one type of spin and an arrow up would be another type of spin. So Pauli exclusion principle tells us no 2 electrons in an atom can have the same exact set of 4 quantum numbers. Only 2 electrons then can occupy an atomic orbital, but they have to have opposite spins. So if we look at helium, for example, both of our electrons here would have the value, or n is 1, L would be 0, so m sub L would be 0. So the 4th quantum number would have to be the spin. Well, if they're both pointed down, then they would either both be negative 1/2, or they could both be plus 1/2. Same with if they were both pointed up. So that can't work because they would have the same set of 4 quantum numbers. However, if they had opposite spins, then one of them would be 1, 0, 0, positive 1/2, and 1, 0, 0, negative 1/2. So in an orbital, electrons have to have opposite spins. Now, this idea of spins also leads us into paramagnetic versus diamagnetic. Paramagnetic means they contain the net unpaired spins and then are attracted by a magnetic field or a magnet. A diamagnetic do not contain unpaired spins and are slightly repelled by a magnet. So if both of our electrons are spinning the same direction, then we're going to be paramagnetic. They're unpaired. If they are spinning in opposite directions, then it's diamagnetic. Measurements of the magnetic properties have provided the most direct evidence for specific electron configurations of the elements. A useful rule is that if it's an odd-numbered electron atom, say you have 5 electrons, you will always have an unpaired electron. But an even number of electrons may or may not be all paired. You would have to see based on the orbital notation. The shielding effect. So why is 2s lower in energy than 2p? The electrons in the n is equal to 2 are being shielded from the nucleus by the electrons in n is equal to 1. The important consequence of the shielding effect is that it reduces the electrostatic attraction between the protons in the nucleus and the electrons in the second energy level. The electron density of the 2s is greater than the 2p near the nucleus. So it has less energy. It's more penetrating towards the nucleus. The 2s is less shielded than the 2p. So if you look at the diagrams of the 2p, we actually see that it squeezes in close to the nucleus. So the idea is that your electrons are probably not near the nucleus, whereas the 2s, it could be near the nucleus. So in other words, the less energy is required to remove electrons from the 2p than the 2s, because 2p is not quite held as strongly by the nucleus. That electrostatic attraction isn't as strong. Huns Rules. So Pauli's exclusion principle would allow 2 electrons to fill the 2p orbitals in any way. But we find that this is not the case in reality. Huns Rule says the most stable arrangement of electrons in the sublevels is to have one with the greatest number of parallel spins. So we fill one orbital at a time before we pair, and the electrons must spin the same direction. So if we think about the p sublevel, it has 3 orbitals. And we would put one on each line, as Pauli exclusion principle states, before we would pair up. all three of those electrons have to be going the same direction. So we could draw them going up, or we could draw them all going down. But they have to have the same spin because Huns Rule says that that's the most stable arrangement. Alright, so some general rules for assigning electrons to atomic orbitals. Each principal energy level, n, contains n sublevels. So if you're on the first energy level, you have one sublevel. The second energy level, you have two sublevels. Each sublevel, L, contains 2L plus 1 orbitals. So if you're on the first, or if you're in the S sublevel, you are 0. So 2 times 0 is 0, plus 1 is 1. So you have one orbital in the S sublevel. If you're in the P sublevel, then L is 2. 2 times 2 is, if you're in the P, then L is 1. 2 times 1 is 2, plus 1 is 3. So the P sublevel has 3 orbitals. No more than 2 electrons can be placed in each orbital. The maximum number of electrons that an atom can have in a principal energy level then is 2n squared. Remember, n squared tells us the number of orbitals, and if 2 electrons can go in each orbital, then 2n squared tells us the number of electrons. So calculate the total number of electrons that can be present in the principal level for which n is 4. So we would say 2n squared. So 4 squared times 2. 4 squared is 16, times 2 is 32. Write the complete set of quantum numbers for each of the electrons in boron. Well, boron is B, and it has 5 electrons. So if n is equal to 1, then L has to equal 0. So my m sub L has to equal 0. And my m sub s is going to be plus 1/2 for one electron, and then minus 1/2 for another. So we would say the first 2 electrons are 1, 0, 0, plus 1/2, and 1, 0, 0, minus 1/2. So then if n was equal to 2, L could be 0 or 1. So my m sub L would be 0 for the L0, and my m sub L would be -1 or 0 or plus 1 for L equals 1. My m sub s is still plus or minus 1/2. So my third electron would be 2, 0, 0, plus 1/2. My fourth electron would be 2, 0, 0, minus 1/2. And so my fifth electron would be 2, 1. Now I have some options for that third quantum number, and it doesn't really matter which one I choose. And then I can either do positive or negative 1/2 for the spin as well. So these last two don't really matter unless we start adding more and more electrons, then we want to make sure nobody has the same set of 4. Alright, so to summarize the ground state electron configurations, no 2 electrons can have the same set of 4 quantum numbers, Pauli exclusion principle. Each orbital can be occupied by a maximum of 2 electrons. They must have opposite spins. Most stable arrangement of electrons in the sublevel is the one that has the greatest number of parallel spins, Huns Rule. Atoms with unpaired electrons are paramagnetic, and those with paired electrons are diamagnetic. The hydrogen atom, the energy of the hydrogen atom only depends on the energy level, N. But if you have more than one electron, it depends on both the energy level and the sublevel. So N and L play a role. A many electron atom is filled based on figure 7.24, what we call Aufbau's principle in Chem 1, reading along the diagonal lines. Electrons in the same energy level, their penetrating power, or the proximity to the nucleus, decreases in the order of S to P to D to F. Alright, so the build-up principle. As we add more electrons, what happens? So the Aufbau principle says that as protons are added one by one to the nucleus to build up the elements, electrons are similarly added to the atomic orbitals. This will help us understand and predict properties of the elements in our next unit. The noble gas core shows brackets of the noble gas element that most nearly precedes the element being considered. That's something that we cover in Chem 1, so hopefully you'll go back and review. Transition metals have incompletely filled d sublevels or readily give rise to cations that have incompletely filled d sublevels. Lanthanides, or rare earth metals, are incompletely filled 4f sublevels or readily give rise to cations that have incompletely filled 4f sublevels. The actinide series is the very last row of elements, and they're not really found in nature because they've been synthesized, so they're man-made mostly. Okay, so write the ground state electron configuration for phosphorus. So phosphorus has 15 electrons. So we would say 1s2, 2s2, 2p6, 3s2, 3p3. Write the ground state electron configuration for palladium, which is Pd, and it has 46 electrons. So we would say 1s2, 2s2, 2p6, 3s2, 3p6. Then we'd have to go to 4s, go back and pick up 3d, continue to 4p, then we're going to jump down to 5s, and finally 4d8. Alright, so now we're going to write the noble gas configuration for uranium. So uranium is number 92 on the periodic table. So the noble gas that would come before 92 would be Rn, because that one is 86. Remember, noble gases are group 18. So uranium would be in row 7 if it was placed back into the periodic table. So we're going to do 7s2. Then we're going to jump down to the actinide series, and the F block is 2 less than the row it's in. So it would be 5F4. Now, using the F block is going to take some practice, just like the D block did. All right, tungsten is W. Tungsten is number 74. So the noble gas that comes before tungsten is xenon. Tungsten is on row 6, so we would say 6s2. Then there's a little notation in our periodic table to say jump down to the F block, and the F block is 2 less than the row it's in, so 4f14. Go back up to the D block. Now that's 1 less than the row it's in, 5d, and tungsten is the 4th one over. Alright, so 2 groups actually have exceptions to the electron configuration. Group 6 and group 9, or group, not 20 and 9, group 11. These have almost half-filled or almost filled d sublevels. It's actually more stable to have a half-filled or filled d sublevel, so they'll actually take 1 electron from the s orbital before to from the s orbital that comes before it to fill or half-fill the d sublevel for stability. So if we look at chromium, chromium's noble gas configuration would be argon, 4s2, 3d4. So if we were to look at the orbital notation, we would have 4s and then 3d, so chromium is 1 away from being full. So it's actually going to take one of the electrons out of the 4s and put it into the 3d to half fill the 3d. So this type of situation is a little bit more stable. So we would have to go back to the electron or the electron configuration or noble gas configuration and change it to 4s1, 3d5. So you have to watch out for the group 6. Group 11 does something similar. So if we look at copper, copper's noble gas configuration is argon, 4s2, 3d9. So if we look at the orbital notation, one on each line, and then we would go back and pair up, but we would be one shy of filling the 3D. So copper actually takes one of its electrons from the 4s and fills the 3D. So we'd have to go back up to our electron configuration and change that to say 4s1, 3d10. So those are actually ground states for groups 16 and 11 because they're more stable that way.